Hello, welcome, Peyman.
Thank
So,
you.
Peyman is going to give a presentation about the two-tower approach or personalized product. Yeah, you can start, Peyman.
Okay. Can you hear me fine?
Yes.
Yeah, sure. Okay. My name is Peyman. I work as a staff engineer in this data science discovery tribe at Trendyol. And today I will talk about the structure of a recommendation system, how modern recommendation systems are generally designed, and how neural networks are used for collaborative filtering and personalized recommendations. I assume that most of us are familiar with the importance and use cases of recommender system. However, as a reminder, in many different platforms, including e-commerce platforms, two of the most important machine learning algorithms that drive the operations are item-to-item relations and user-to-item relation estimation algorithms. For item-to-item algorithms, when you visit any product, there is almost always a section that recommends similar products and alternatives to you. When you proceed to buying a product, in many cases, if not all, e-commerce websites will provide you with a section that recommends similar along with complementary products. And these are the use cases for item-to-item relations. And for user-to-item relations, the key is to do the personalization, and the website recommends products that not only are related to the page that you are looking at or the item that you are trying to buy, but also is tailored to your specific needs based on the information that are available from your previous activity on the website and other static information. So today I will provide a brief description of recommendation algorithms, three-stage recommender system design, efficient item retrieval through two-tower architecture, and how we do it at Trendyol. Generally, there are two main classes of algorithms for recommendation systems, content-based and collaborative filtering algorithms. There is also a third type of algorithms, hybrid approach, which is a combination of the two other approaches by weighting, switchings, and there are many different variants to them. For content-based filtering, the main algorithm works like this. Items are grouped according to item profile. That is, there's a group of items that are related to each other. For example, if you're talking about movies, the profile might be created based on the director, actors, the topic of the movie. If we're talking about books, the profile might be based on the author, publisher, the genre of the book. Or if you talk about the e-commerce products, the profiling might be based on the category, brand, price bracket, descriptions, and many other factors that describe the item. Then, for each user, based on the past interaction and the items that user has positively interacted with, a list of candidates are generated, and it is generated such that the latest, the most recent items that one user is interacted with are used as references, and the items that has the same profile as the most recent items of the user are used to create a candidate list. Then at a later stage, any sort of ranking algorithm is used to provide the user with the most relevant information. Here, the key is that only a single user's interaction is used to create the recommendation list. And the main information used to drive the item-to-item relations are item profile information. for collaborative filtering, the main idea is to use the user base's interaction information to calculate the score between a user and an item. So basically, it's a user to item relation algorithm. And to do so, the main idea is to average the rating or the interaction value of the users similar to the target user. And that average would be predicted rating or interaction value for the target user. And based on that average value for each of the users, we create a recommendation. Here, the key is to find the neighborhood of similar users that are similar to the target user. Then calculate the averaging. And there are different methods. There are model-based methods. There are memory-based methods. However, these considerations and steps are sequential nature of the user item interaction is taken into account. Neural networks, specifically two-tower algorithms for retrieval that we are going to cover today, are context-aware and sequential based on the variant. So serving personalized recommendation is not an easy job, specifically when you think about the scale of the problem. Generally, you're trying to recommend items from a pool of millions of products to user base, again, of millions. That's at least the case in our case in Trendyol. Now, when you consider the scale of the problem, what you have to do is to calculate for each user and item pair and a score for at least users that are currently active on the platform, which is on any given minute, probably on the scale of thousands, and for the products of the scale of millions. This is too much. It needs a lot of infrastructure, and it's costly in terms of calculation and infrastructure cost. To mitigate the cost problem and also meet the acceptable response time requirements for a good user experience, the recommendation process is broken into three main sub-steps. In candidate generation, generally, what is done is to filter the pool of millions of items into something to the order of thousands of items. Here, the main optimization criteria is recall. So the precision and the exact ranking and scores are not required to be very accurate or too accurate, but recall should be optimized. And the final scoring is left to be handled in the next steps. This usually has a higher time to be done, so you don't need to do it very fast, like in the order of minutes, in the order of seconds. So you can assume that you can do this step in an order of minutes and be fine in terms of user experience. So you can do filtering for millions of items. Then at the pre-rank stage, more accurate models are deployed. Precision is something that is more of a concern here, and more information is usually used for user and item, both of them, for each pair, to have a more accurate score. And finally, in ranking stage, the most accurate models are used here. And you can do that because when you reach out to the ranking stage, you are just handling at most hundreds of items. for each user. So you can use many additional features. The complexity of model might be higher. And again, despite all of this, you can achieve a very good response time. There are some additional cases in recommender system design. Sometimes there are also re-ranking stages, but those are generally used for consideration, like business consideration for re-ranking. For example, to increase the diversity of the items provided to the user, or filtering for inappropriate items if that's an issue in the platform. However, the main three parts that are that machine learning algorithms are used are these three parts that we provide. Now let's take a more closer look at matrix factorization and use the general matrix factorization paradigm as a starting point for two-tower candidate generation model. Given the user item interaction matrix, which is on the right side of the page, the goal is to decompose the matrix into two sub-matrices. One is representing user embeddings, and the other represents the item embeddings. But the decomposition is done such that the product of user embeddings and item embeddings approximates the user item interaction matrices. So if you look at how each element of the user item interaction matrix are ij, and how they are related to user representation for user I, which is ui, and item j, one can conclude that during the decomposition process, the dot product estimates the interaction value or the rating value for user item pairs. Also note that here we only use the interaction information. There is no additional auxiliary information, or there is no temporal information that can be incorporated in the classic form. Now let's try to estimate the user and item representations with a neural network. So this is a common practice to have a sort of embedding coming out from a neural network. So here, if you look at the formulation to approximate the rating, one can argue that user embedding UI can be calculated through a neural network. Let's call this one user tower. And the same is applicable for the item embedding. A second neural network might be trained to calculate the item embedding. Let's call the second one the item tower. This is the general scheme of naming in the retrieval space. Then to train the items, what we need to do is to just calculate the product of the embeddings that come from user and item latent vector, and then just use cross-entropy loss to optimize the weights through backpropagation and gradient descent. Basically, we are doing a classification problem here. You should do a classification problem, but it is reformulated to handle the millions of the classes here. Then the probability of each class can be used to filter for the top k most probable items, and that's the list of candidates that we are looking after. In terms of the information or features that one can fit to the user tower, the very basic is user ID. This is what matrix factorization generally uses. Only user ID is used for user information. However, an interesting side effect of using neural networks is that you can add easily additional pieces of information, such as history of not just interaction, but in the e-commerce space, if you're just looking for the click as the interaction proxy, you may also add order, maybe also adding favorite items. Also, you can add the static information for each user. in terms of location, demography, anything that you have in the platform. Search history might be added, which are usually handled separately from the click views or views in the e-commerce space. And this is extendable to all the different platforms that may use item recommendation. And then adding all of these doesn't add actually complexity in terms of training the algorithm. Again, you use backpropagation, and again, the gradient descent finds the best set of parameters that efficiently combines the provided information to create good user embeddings. Same as user tower. In the item tower also, we can add multiple sources of information along with interaction information. Again, in matrix factorization, the only information that is provided here is item ID. However, one may also use unstructured data regarding the item, title, description, image, or any other descriptive information that is available, and easily integrate them to the same model and iterate over fast. As you can see, moving to neural network-based approaches opens a lot of possibilities. You can basically, in the example of descriptive information like text information or image information, you basically are combining the filtering, collaborative filtering with content-based filtering, and let the network decide how to combine these two algorithms in the most efficient way. The only thing number of parameters is the embedding matrix that embeds, that is the number of users and the number of items. For each of them, you need to have a table of vectors. And in the simplest way, for different auxiliary information, the combination of additional information with user interaction data is done through either average pooling or concatenation. Let's look at a more sophisticated architecture. Here, in an example of a video recommendation system, there is an attention layer in the item tower. And this attention layer is optimized, or during the training is optimized to efficiently incorporate image and other video-related temporal information to the user item tower. So from this simple architecture, doesn't have any sort of complex attention mechanism, only uses pooling. One can easily add also attention layer here. And to incorporate the additional information regarding the images or other video related features, you don't need to train from scratch. One can use any sort of pre-trained algorithm and also provide the embeddings of those pre-trained models here. And this offloads a lot of complexity to pre-trained algorithms. Or in the example of, for another example, in the multi-interest network, the user tower is more complex compared to the item tower. Here, each user is represented not only with one embedding, but instead with multiple embeddings. And the reason is a user's recent preference or needs might be diverse. Let's say a user planning to buy a shirt, a pair of shoes, and at the same time is trying to buy an electronic device like a headphone. Therefore, if you use the browsing history from these different categories and try to embed them into one embedding vector, you are basically averaging over the most frequent item or category that the user has been browsing recently. However, you can easily add a layer to create more than one representation, which is done here to the multi-interest extractor layer. In concept, it sort of does a clustering of the embeddings, and instead of averaging all the history vectors into one vector, it creates multiple clusters. Usually it's topped at 5 and at most creates a couple of different vectors. For each user, multiple embeddings vectors are created, and each vector corresponds to a different view of user's recent history. Therefore, when you are calculating the score for user item pairs, you can have more than one list for each user and look at the scoring of them and decide how exactly combine them. Here, the user tower is modified, and let's take a look at a different example. So far, what we're trying to cover is the flexibility that using neural networks and two-tower architecture provides for the data scientists to combine them and create a very tailored, need-specific architecture for retrieval stage. Here, instead of recommending single items, the architecture tries to recommend collections of items. A collection might be a bunch of books from a specific genre, or playlist of a couple of songs in any streaming platform, or a collection of items in an e-commerce platform. A very naive way to combine to create such a system is to combine an average item embeddings that have been calculated from any of the previous algorithms or more classical algorithms and call it a day. However, an item may have different utility, a different meaning when grouped with different items. Say you want to recommend a playlist, and you have the same song appearing in two playlists. One, greatest hits of the year. The other one, best songs of the country music, for example. Now here, when you think of it, the same song has a different meaning, different utility in these two collections. And using the same vector and averaging doesn't convey the whole meaning. Now here, the architecture adds an aggregation layer on top of the normal embedding layers that are present in the previous algorithms. And this aggregation layer provides the possibility of using collection interaction information and at the same time have item embedding information. So basically, you can learn embeddings for the same item regardless of where it appears, and use the collection level interaction to create your retrieval system. So again, what you're looking at is the flexibility of the two-tower architecture and how it can be tuned based on the need. Now let's take a look at the real-world example that we developed in Trendyol. Here, the goal is to provide the user with the most relevant item as soon as they enter the application, as soon as they land in the homepage, before any sort of search activity or browsing any item. So here, what we are trying to achieve is to use the previous history of the item plus the most recent history and give them something that might be the most relevant, and they can jump directly from the homepage into the buying an item. So as we explained so far, the two-tower has one component that embeds items and one component that embeds users. For serving this model, what you need to do is to create a database of vectors. if you think of it, items property and features doesn't change by time. So when you have a network that embeds items, you can just use it as it is without any update in real time. So you create a database of item embeddings using the trained model, which is trained in offline mode. So already you are offloading a huge amount of computation from online serving scenario to the batch offline scenario. So say you have millions of items, you create millions of item embeddings. They are not going to change until you update your model. And you just add them to the fast retrieval system, which the main component here is the vector DB. Then in the online scenario, whenever the user enters the system, the only thing that you need to calculate right now is one embedding for one user, and then make a query. Ask the fast retrieval system to give you the top K highest scoring items. So again, the point that I'm trying to highlight here is that through the two-tower architecture, you are isolating a huge amount of calculations to be done offline and in batch jobs. And you're just doing a search and a query plus one, usually a small network with a bunch of simple features that can be streamed near real time. The fast retrieval system, vector DBs, has a lot of technical complexity in them to be able to do the query very fast and near real time. However, it is doable. We've done this through our system. It's working in the order of a couple of seconds since the last action and updates the candidate list. And the rest of the system, based on the page that you are, the part of the platform that you are, ranks the system and provides you with the final recommended list. That's it. Here also you see a slightly more convoluted architecture of our system, but it's basically the same architecture. But you see that we use Spark and different endpoints, TensorFlow for our serving, and Kafka to stream the candidate list. That's the content that I wanted to provide you. If you are any question, I'm happy to answer them. Furkan, I think you are on mute. I can hear you.
Thank you for these great insights in these recommender systems.
Thank you for the opportunity.
So in the end, you are trying to predict the human behavior. You are trying to recommend some items. So that's why I don't know how there's an item based and maybe user based. You are combining them. It is a high hybrid.
Yeah, this is a user to item approach. So if you remember at the beginning, all the collaborative filtering approaches basically do user to item relation estimation. There is a subcategory, a sub classification in terms of item-based collaborative filtering and user-based collaborative filtering. But in two tower, it's basically combined user to item estimation.
So is there any possibility that users can manipulate that recommendation? Because I guess there was in the previous approaches, some people were
actually it's interesting that you pointed at that. That actually that's one of the major problems that we faced during our first try. Any machine learning algorithm is as good as the data that you feed it with. And in case of neural networks, it's more pronounced because it just optimized for whatever data that it sees. And in our case, actually, we faced the same problem. There were a lot of fraudulent clicks in the system, like one product, despite that hasn't been any order recently, or the product that hasn't been a top seller or on average wasn't a good seller, had a lot of clicks and views, a lot of clicks that only ends with just viewing the product without any order, without adding to basket and so on. And in our first iteration, that was one of the major, those type of products were one of the major category of product that our system were recommending. By backtracking what the system is recommending and looking at the information for those products, we conclude that these are the things that you have to filter for. So basically, there is a sort of cleaning in the data, and also a sort of you need to apply sort of frequency adjustment. Not sure if how familiar you are with word-to-vec training.
Yes, I have some.
Yeah, there also there is a frequency adjustment if you remember. If you don't adjust for the long tail distribution of the words, the model learns to predict the most popular. So here, wherever that you have a sort of long tail distribution of items, which is the case for us, if you don't adjust this distribution and clean up for the items that are not actually popular, only look popular, you will be at the end train a model that recommends only those items. And in our first iteration, we did face the same problem. We did clean based on some averaging, comparing to the average view, filter based on the orders for the past recent months. So there's a huge step of data cleaning, but that's always the case.
Yeah, also there are some other behaviors just includes the item-based similarity as well. It also averages these manipulations, maybe the product-based matches.
The other behaviors that, as I specified, are not covered, right?
Right.
Yeah, we do have a couple of different components in our system during the collection of data that they pinpoint fraudulent activity in terms of view. So if the item is itself receiving a lot of views from a bunch of users, so sort of a click farm, if you will, or if the item description has any sort of misleading information or the pricing is off. There are a couple of different teams and the different components in our pipeline that clear for them. So
it is actually another model maybe predicting it is fraudulent or not.
Yeah. There are a couple of different components in our pipeline that start from the streaming, collecting data, to the level of aggregation, and we look back from a scale of a couple of hours to monthly data, also 3 months data, to pinpoint activities, products, and users that looks to be off. I'm not going to call them fraud, but they're not genuine or organic behavior. In the development of this model, the frequency, the long tail frequency of both genuine popular item and the items that during the clicking had sort of a off behavior were the major problem. We didn't face anything else.
Got it. Okay. So yeah, it looks we don't have any other questions. So thank you again for your great talk. Hope to see you again in our future events.
Sure, that would be an honor.
Thank you so much. So we have last session. It is going to start in 10 minutes. I will share the talks so that you can see the room 1 and room this talk so that you can participate the one that interests you. So also at the end of the last session, we will have a quick quiz that will ask a couple of questions, and we have some rewards for 3 people. Yeah. Let me share. Burak is here. Burak, we will start in 10 minutes. We had a coffee break now. We will start 10 minutes later.
All good. Perfect. Thank you.